So I will introduce Weinan Lin from Peking University, who's going to tell us about efficient algorithms with DGAs and their applications to the May spectral sequence.
Okay. So actually today, because recently I've some new discoveries, besides what I've given in my abstract, today I'm also going to talk about something about the atom spectral sequence. So, but yeah, let's start with the originally what I claim to do. I'm going to talk about algorithms with DGAs, and so here is the question, or here is the theorem that if we have a finitely generated commutative DGA over a finite field, then the homology is also a finitely generated as an algebra. And the proof is quite simple and straightforward, that because we're working over a finite field, therefore the images of Frobenius a to the power of p is a set of cycles, and we have that A is a finitely generated AP module. So all P's powers are also they also form an algebra, and A is a modules over AP, and because you have because A is finitely generated, and you consider the powers of the monomials of the generators, but the exponent are going to be capped by P, so therefore it's finitely generated. And the second claim is that C is a AP submodule of A, and that's obvious because AP are all cycles, and is contained in G, the cycles. Therefore, it's G is a submodule of A. And then, since A is a Noetherian and C is and A is a finitely generated, therefore it's a Noetherian module. Therefore, all submodules of a Noetherian module is also Noetherian, which means that it's a finitely generated AP module. Okay, so since A to the P is finitely generated and G is a finitely generated module over AP, then G is itself finitely generated algebra. Okay, and now the homology by definition is the algebra G over its ideal B, and therefore it's finitely generated. Okay, and that's a proof. That's a kind of a long route, but it's not difficult. Okay, so since A is finite.
Sorry to interrupt. Just for the context, I guess I just don't know very much about this stuff. Is this supposed to be like a well-known theorem, or is this your result, or I just don't know like what's previously known?
I'm confused too. I've searched for it, and it's not hard to prove. But I don't find any. I can't find it anywhere. But if you search it on Stack Overflow, you can find a counterexample to this over Q. So I remember that Akio and Parmiri gave counterexamples on the certain question. That's where I can find information regarding this problem. I mean, a finitely generated property of a homology of a DGA. And so yeah, I just want to add that remark that if this is over Q, then it's false. This theorem is false. You can clearly see that this proof doesn't work if it's not over FP. Yeah. So does anyone here know where it's from?
I'd like to ask a question. I don't know where it's from, but what about, are these things also finitely presented? If A is finitely presented, can you say that about its homology?
Yes, so because it's a finitely generated algebra, therefore all the ideals are also finitely generated. So of course, it's finally.
I see. Okay.
Mhm. Yeah, that's just Hilbert, a theorem of Hilbert's, and so we have all these nice things. So if A is finitely generated, I mean, as an algebra, then we can choose a finite presentation of A. And yeah, assume that these Fi are explicit polynomials of Xi, and then and assume we have explicit Yi for the differentials. Then we would like to present the homology similarly, that you present it as a by generators and relations, and you also tell us that what these homology classes are. You also give these cycles. So here's the question. I want the real algorithm, a computer algorithm, which can give us the presentation. Since everything is finite, and therefore there must be a computer algorithm which can give you everything. Okay, and this is like not truncated by any degree, but if A is an infinite generated algebra, then you can just truncate everything by a degree. Then automatically everything is true again. If the generators are spread, I mean, if in each degree there are only finitely many generated, then when you truncate things, it will work again. These algorithms work again. Okay. So before I introduce the algorithms, I would like to give you an example. It's the reason that I do these algorithms. So the problem I wanted to solve is to compute the homology of this DGA. This is my favorite DGA. So X is a polynomial algebra, and then the differential is like the matrix product. Differential Ij is Rkj, and then the homology of this cute DGA is the E2 page of the main spectral sequence. And so you can actually consider a sub DGA of this X. So in my thesis, I considered this sub DGA I cap J up to 7. And so you can obtain the homology of X7. It actually corresponds to the main spectral sequence converging to the cohomology of A7. I mean, A7 is a sub-Hopf algebra of the Steenrod algebra. So this X7 corresponds to that A7. Okay, so this X7 is a finitely generated or presented DGA, and you can find the full presentation of its homology in my thesis. And okay, and how
can I ask a question? What is this Rij? How does that? What element of the dual Steenrod algebra does that correspond to? Or another question?
I know these indices are kind of confusing. It's different from everyone. So this Ij corresponds to C J minus I, and to the powers of 2 to the I.
Cj minus I to the power 2 to the I. Okay.
Mm-hmm. So I use these indices just because the differential looks just like matrix multiplications. And in my thesis, I have a lot of techniques manipulating the cycles. They can look like a determinant of matrix or sub-matrices of R or something like that. And that's why I choose these indices. Okay.
So these are not, necessarily, let me just briefly remark about this. These are not necessarily standard notation for main spectral sequence, kind of like every author has chosen a different one. But like my experience with trying to do the bookkeeping and keep things organized and figure out what's really going on with the main spectral sequence is that this indexing that Weinan's chosen is the best one for that purpose. And it might not be ideal for theoretical reasons, but for just brute force computation, this is the way to go. And it's not the one that I've used in the past. This is a change on my part. So anyway.
Thank you. Then I think I agree with you that without this indices, there's no way I think discover those patterns by of the description of the E2 page of main. So in my thesis, I have a conjecture of all the relations in the E2 page. I mean, all relations up to all degree, and yeah, and I'm able to find those patterns just because of the way I index them. Okay. So next, I'm going to introduce global basis, which is going to help us build those algorithms. So the global basis answers the following question: if in a polynomial ring we have certain elements fi and j and gi, then how can we identify two ideals? I mean, an ideal can have many different representations, and how are we going to identify them? So we want to define a global basis to solve this problem. And to define a global basis, we must have a monomial ordering, and it should be a total ordering of monomials with this property that if m is less than n, then the multiplication does not change the order. And this is important. And there are many examples. Which the first one is you order them by degree, and then order them lexicographically. And the other one is order them by degree first, and then order them by reversed lexicographic ordering. Okay, so once we have fixed the ordering, then we can define the monomial, the leading monomial. The leading monomial is the largest monomial in F. Okay. Now, if you Google the global basis, you are going to find more than 10 definitions of global basis. And here, I'm going to introduce 3 different definitions. The first one is originally my favorite, and after some time, I change my favorite becomes the second one, and now it's the third one. Okay, so what's the first one? So originally, my motivation to use global basis is to present a ring by generators and relations, and therefore I use this definition that I want such a presentation such that I can understand the additive basis of R properly. So a global basis of I is a generating set such that if you exclude all multiples of leading terms, I mean, if you include all of them, then the rest of the monomials projects to F2 basis of the quotient ring, and that's it. And so in some sense, since there are many rings such that the quotient ring are infinite dimensional, and therefore you must find a good way to understand the additive basis mathematically. So actually, originally I used this in my program before I realized it's I realized so I used the algorithm of global basis before I realized that it is called global basis, and it is a well-known thing. So here is the idea. The idea is very simple. That if you consider an ideal xy plus a, xg plus b, and then to form a global basis, you actually need a help of a third element. It's a redundant element. It's not. This is not a minimal generating set of I, but you need this because you want this. You want that the quotient ring P over I can have a basis which basis? The basis is all monomials that's not divisible by any one of them. So if you exclude all multiples of xy, all multiples of xc, and all multiples of ga, then you get an additive basis of R. So it's pretty nice. And you must need the third element. And I can tell you how to obtain this third element. That if you consider xy and xc, there is a the least common multiple, which is xyz. And you multiply the first one by z, and you must multiply the second one by y. And then you add them together, because we are working over prime 2 here, and then the leading terms canceled out, and this is the rest, and that's it. Okay, and now here's the second definition. It's basically the same as the first one, but with a different perspective. So here I define something called LMI. It's the ideal of P generated by all leading terms of elements in I. So I is generated by some polynomials, but if you extract all the leading terms out and form a monomial ideal, I mean, it's an ideal generated by all monomials, then I call it LMI. So if G is a global, so G is a generating set of I, then G is a global basis if and only if LMI is generated by the leading monomials of the set G. And so here's the, so if you think, it's not hard to see that it's equivalent to the first definition. It's just a different perspective. And here's the remark associated with this definition, that if you consider the quotient ring and filter R with monomials, so first you filter P with monomials, and then it induces a filter on R. So the set of all monomials is a well ordered set, because we have chosen a total ordering, and it's also a monoid. I mean, the set of monomials forms a monoid. So you can filter out or filter things with such a set, and then you get an associated graded algebra. So the associated graded algebra is defined, with this filtration. And here less than m just means that you kind of abandon all the monomials beyond m, and then the conclusion is that the associated graded algebra is P over leading terms of G. So in some sense, the global basis it's not a minimal generating set of I, but it is a minimal generating set of the relations in the associated graded algebra in its sense. Okay. Next is I'm going to introduce the third definition, and this is something I really like, and it's going to be very important because in the end I think I'm going to mention a new algorithm I found to compute the E2 page of atoms super fast. Okay, so here we define something called the CGG. The CGG module is basically the annihilator. So it's like it can kind of think of it as a matrix. It's all the matrix such that the row matrix multiply that becomes 0. So yeah, it's all AI such that the sum of AI GI is 0. And okay, and here is the definition of CIJ. So if you consider the CGG of M of two monomials, it's going to be simple. It's just that you find the least common divisor, and so the special case is that if Mi and Mj are co-prime, I mean inside the polynomial ring, then the thesis is going to be boring. It's just Mj Mi plus Mi Mj is 0 because the ring is commutative. Okay, and there's a theorem that the Cij generates the CGG of monomial ideal, that if you have an ideal generated by monomials, then the CGGs are just all Cij, and that's it. And they actually form a global basis with certain monomial ordering. And here's my third definition for the global basis, that G is a global basis of I if this Cij leads to a generating set of CGGs of G, which is the kind of the annihilators of this G1, G2, Gm. And so it's wonderful that in order to compute the annihilators of the sequence of Gi, you just consider each pair of them, and quickly you can expand that. So the story is that the Cij is kind of the leading terms, and you add some garbage term, and you can do it pretty fast, and you get CGs of G. So sigma ij tilde actually forms a global basis with the monomial ordering. So it's a global basis for the CGGs of a group of G. Okay, and so we haven't talked about how to, given an ideal I, how to compute the global basis of the ideal. And so there's an algorithm called Bgas algorithm. I think his Bgas thesis is around the time that my PhD advisor Peter May published, finishes his PhD. That's just a fun fact. So the algorithm is pretty simple, that you start with the generating set of I, an arbitrary generating set of I. And then for each pair, you try to annihilate the leading terms, and you produce a new element. And then I'm going to reduce that by G. Here, reduce means that if any summand of this element is divisible by certain leading terms in G, then I'm going to replace that term by the rest of the terms of Gi. So if the leading terms of Gi is of G1 is M1, and if I find certain M1 somewhere here, I'm going to replace M1 by G1 minus M1. Okay, so it's like the rest of the terms in G1. So you each time you annihilate, I mean you cancel out the leading terms of pairs, and then you compute the result and do the reduction, and if it's non-zero, you add it back to G, and you keep doing this until for all pairs. Now when you reduce this, it is reduced to 0. Okay, so that's the algorithm. It's quite straightforward. And I really like this because each time you just consider a pair, and in the end, magically you get the CGs of the whole sequence. Okay, so so what can we do with global basis? So first we can have a unique presentation of a quotient ring. I mean, finally general kind of like general algebras in terms of generators and relations if you fix a monomial ordering. I didn't mention there's something called reduced global basis. If you have a global basis, you can further reduce reduce that. I mean, the original list of generators might have some redundant, and you can remove some of them, and you get something called reduced global basis. And if you fix a monomial ordering, the reduced global basis is going to be unique. So if two people agree on one monomial ordering, then the presentation of the algebras is are going to agree. So that's good. And then you have a unique presentation of elements in R. So remember, in my first definition, there is a kind of additive basis, kind of like standard additive basis determined by the global basis. Therefore, you have a unique presentation. And then you have a fast computation of subalgebra of R. I don't have time to cover this, but you can find those algorithms in a kind of like textbooks or about computational commutative algebras. Okay, and you can and then this is the most important. You can compute CGGs. So if you have in a algebra, if you have certain elements and you want to compute the CGGs of them, there's a very fast algorithm. And here I only told you that you have a fast algorithm for CGGs of a global basis. Then what about arbitrary M element here? And the method is quite simple. You just form a global basis generated by this element, and then you compute the CGGs of the global basis. And then because the two ideals, I mean the ideal generated by this GI and the ideal generated by the global basis, they are the same ideal. Therefore, you have matrices converting one to each other, and then there's a kind of a magic formula which tells you what the CGGs of the original sequence is in terms of the CGGs of the global basis. They expand. Okay, now let's do a fun experiment about CGGs. So first, we start with a assume that A is a commutative DGA, and we start with a non-bounding cycle C, and we assume that the CGG of C is Yi. So which means that C times Yi equals 0, and this is the generator of the ideal. And then you compute the CGG of the sequence. So it's going to be, it's going to be a kind of a matrix because there are n elements of them. So I'm going to write all the generators of this CGG in terms of a matrix. So the CGG of this list is a span of columns of the matrix. So what can we say about them? So I think some people might think of the like messy product. You have C, and then you consider all the annihilators, and then you consider the annihilators of annihilators. Then you can form a kind of a universal triple matrix messy product, and maybe you can compute it or do something with it, and that's true. But today I'm going to talk about my first algorithm for computing homology of DGAs. It's related to this, that if you start with A and form a polynomial ring B, so B is A adjoined with X, and here X, the differential of X is given by the non-bounding cycle C in A. So the interesting thing is that the CGGs of C correspond to the new generators of the extended DGA, and the CGG of CGGs correspond to the relations among the generators. And more precisely, if we filter this B by powers of X, then I can compute the associated graded algebra of B. So B, here I'm working over F2. I forgot to mention here. And so you're working over F2, of course, X squared is a cycle. So it's something special here. And then you have those GI. Those GI correspond to YI. And the relations given by the obvious one, C equals 0, because C becomes a boundary here. And then we have some additional relations. They correspond to the relations. Sorry, here new relations correspond to the CGGs of YI. So YI correspond to GI, and the relations among YI correspond to the relations among GI. So and that's it. And here is a kind of a special relations, just because we are working over F2. So if you work over Q, for example, I mean any field of characteristic 0, then the thing I said here is completely true. That you don't have this special, element X squared, and you don't have this kind of special relations. So if you walk over Q, then YI truly correspond to all the new generators, and CGGs of Y correspond to the relations. Okay, so I think this is awesome, and you see that this theorem kind of gives us a way to compute homology of B from homologies of A. And given that B is A adjoint with X, so here I do not allow X to have some relations involving A. So I want X to be a free variable here. So this theorem have some restriction, but we can iterate this theorem to compute a homology of a polynomial DGA. I mean, if it's a polynomial, then it's kind of A adjoint with X, adjoint with Y, adjoint with Z, and it's polynomial. And but some people may ask the question that here you get the presentation of the associated gradient algebra. You got extension problems and how to solve this. And the first solution is to solve it kind of half manually. And I want to tell the story of me solving the main spectral, computing the E2 phase of the main spectral sequence. The way I solve the extension problem is that it's because that I have a conjecture of the homology of sub-DGAs of X. I kind of write all the homologies out down in all degrees, and I organize for the homology of the partial of the sub-DGAs. I remember that one of them involves like 16 patterns, and it's very combinatorial. And for each one of them, I wrote down a chain such that the differential of the chain is exactly the relation. So yeah, you can imagine that it is very painful. I have gigantic summations, a kind of a magic chain such that the differential is the relation. Because you know that this process is not canonical, they kind of look ugly, but that's how it works. I have proved some of the differentials. Therefore, I'm able to prove like that in my conjecture, all the relations, many of the relations are true in all degrees, but some of the relations, what I cannot prove is that they are all the relations that we need to present the E2 phase of May. And but this algorithm tells us that if you solve these extension problems, you get the algebra, and I just compare this associated gradient algebra against the actual, against my conjecture, And because I proved that those relations are indeed relations, I just don't know they are all the relations, but the associated gradient algebra kind of give an upper bound of the relations you need. And so that's my original way of solving the extension problem, because I secretly know what the extensions are by conjecture. And but it's painful that you need to kind of write down have to write down the relations as boundaries. Okay, and then after I graduate, I came up with a fully automatic computer program to solve the extension problem, and the solution relies on a conjecture. So it's actually, I find that the conjecture is often true. It kind of measure the complexity of a DGA. So here's the definition. I define IB, which is the ideal of X generated by all boundaries of generators. So you can see easily that it's actually the ideal of X generated by all boundaries. So the boundaries is the ideal of the cycles, but it's not ideal of the whole algebra. But you can just expand it to an ideal of the whole algebra, and you can find that IB, you can filter X by IB and get kind of a spectral sequence converging to HX. I mean, you get associated gradient algebra of X, which is the summation, which is the sum of all this, and this conjecture tells us that the spectral sequence converges, is concentrated in 0 degree. So that it means that the homology of X is exactly the kernel of this map. You consider X over the ideal generated by boundaries, and you take so here the map here is the differential, and so how to use this to solve extension problems. So imagine that I have obtained an associated gradient algebra of HX. Then I think I may need a pen. So all right. How to annotate? So assume that you have a monomial M here, and maybe I want R here. I have a relation R in the associated gradient algebra of HX, and then I can project it to X over IB, and then I find that it's after I can concatenate it with this map, it's not 0. Then I know that there must be a hidden extension. I have to add some garbage trash term, so that after this map it becomes 0. So basically I just have to compute X over I. So it's very easy to compute X over X is polynomial, and IB is just some polynomial. So it's very fast to compute a global basis for this guy. And then this theorem kind of tell you that HX can be embedded into this kind of simple looking algebra, and you just use that to detect whether a relation it's actually a relation or not. So, but this is a conjecture. This is not something I know it's true. But what we can be sure of is that this map must be 0. Therefore, I use the linear algebra. I compute all the relations such that this map, after this map, it becomes 0. So if this sequence is not exact, then it's possible that I can get 2 relations that this tells me that such that this tells me the two relations are both candidates of the extension problem. But if the conjecture is true, then there's always only one candidate, and it's the only possible extension problem. And I use my computer to check, and the computer keeps telling me that there's only one candidate. So the program is kind of verifying this conjecture at the same time, and also solve the extension problem at the same time. So,
Weinan,
there's
a question in the chat from John Rovness.
Okay. Yes, I think this is injective, and at least so right now, because of the automatic machine, I've computed the presentation of the E2 page of main up to degree T less than 1000, and so I have a very long list of generators and relations, and so I've checked everything under this degree. At least this is injective within the degree 1000, and that's it. And I want to tell you that because of this, the program is very, very fast. I obtained the E2 page of main up to 1000 just within 1 second, and the list contains a very long list. It may ranges over 1000 pages of PDF if you really want to write them down. But
so you said you said 1000 in 1 second, but like, what's the growth rate? I mean, what if you gave it an hour? How far would it go?
I want to tell you something because I was a little bit lazy. Therefore, when I index the generators, I use Rij, and therefore, if the indices are bigger than 10, then I kind of have a problem in my program. So I didn't check, but I believe the complexity is kind of exponential, for sure. And but up to 1000 is still very fast. I believe that if I just because right now I have a new project to go, but if I want, I think I can obtain up to, maybe if I'm optimistic, up to 2000. There's no problem of that because there are not that many relations in this range. I think it's a few thousand. I think the problem that it is long is not that the number of relations is long. It's because each relation contains many summands, many monomials, and that which makes it very, very long. In some sense, I think, I don't know, somehow I feel that the main spectral sequence, the elements in main spectral sequence are kind of as long as possible, or like all the differentials, there are many summands, and it causes a lot of trouble too. Okay, maybe let me move on. How to close the chat. Okay, can you see it now?
Yeah. Yep.
Okay, great. So consider a general EGA over F2. So our goal is to obtain the homology, and so previously our previous algorithm only works with polynomial DGAs, and so if the DGA is polynomial, then my first algorithm is the fastest. It's super fast. So if you apply the general algorithm that works with all DGAs, it's not as fast as the first algorithm specialized for the polynomial one. So if you have a general DGA, then assume that it has a presentation like this, then I'm going to define something called homological monomial ordering. ordering. And it's actually, the whole idea is actually quite simple, is that I try to add some kind of dummy variables. I'm going to call this H1, HM, and then B1, BM. So I'm going to change a presentation that I add some HI and BI, and actually here I is kind of a sub idea of J, and I want this to be a presentation of A again. So and the idea is simple, is that I have to find HI in the original presentation. So it's kind of elements of A. And then I identify HI with a little HI with the bigger HI. So this HI and BI are redundant. They are just, so by the ideal J, after quotient over J, they just becomes the same as certain elements in Xi. So I also have BI here inside this, such that BI plus BI is also in J. So my goal is to realize the cycles by the subalgebra algebra generated by HJ and BK, and then I want the boundaries to be generated by those BK as an ideal of G. So that's my goal. I want to find such a presentation, and I'm going to choose something I called homological monomial ordering. The ordering is something like this. If I have monomial M and L, so M is a monomial in X, and N is a monomial in H. And L is a monomial in B. Then M and L is less than or bigger than M prime, N prime, L prime. If you compare the degree of M first. So you compare the degree of M, and if they are equal, then you compare the degree of L. But you reverse that, and then you compare M and L. Lexicographically here. So you first order them by degree of M, and then order them by degree of L reversely, and then you order them because you want to get a well ordering. So you have to add a complementary ordering finally. Okay, so the idea is that after this monomial ordering, I can read off the homology of A from the presentation. So I can get a presentation of HA from the presentation. I can obtain a presentation of HA from the presentation of A, and because of this monomial ordering, each time you might see some HI, and if the leading term contains only HI, then you can prove that the rest of term only contains those HI or BJ or BK or other stuff. And to read off the presentation of HA, you just find all terms such that the leading term contains only HI, and then find those terms, and then it delete all the semantics with BJ, and that's it. So basically, the idea is that the presentation of A contains kind of a presentation of HA. And so the difficulty of the algorithm is that you have to find this HI and BI, and I use a very interesting and small theorem. There's a very interesting theorem that helped me find those BI. So the theorem is like this. Assume that I is the augmentation. I is augmentation of A, and I Z is augmentation of Z. And then we can show that A over A IZ. So IZ is an idea of Z, but not an idea of A. So you have to multiply with A to obtain an idea of A. And then you consider the differential. This is going to end up with this. And I think there's a ground field here. The interesting thing is that this is exact. And this A over AZ, it contains all powers of. It contains all powers of A, and they are cycles. So it's a kind of a finite thing. So by this kind of exact sequence, you can obtain the indecomposables of the boundaries as an ideal of the cycles. So yeah, so with the help of this, I can discover those BI, and then I can and then to obtain HI, I just kind of discover the relations among those BI inside A, and then you can read off the HI from those relations. I mean, kind of CGGs of those BI. So I mean, I think I'm kind of running out of time. What's the end
we started a little bit late, but maybe finish it up in just a couple of minutes.
Okay. Now I'm going to in the end, I'm going to show you something exciting that some people might be very interested in the CGGs of elements. If these elements are in a commutative algebra A, I mean, maybe finitely generated, this algorithm in the computational commutative algebra, I mean, in the theory of global basis, it's very, very efficient. I mean, the existing algorithm, I think it's kind of as efficient as possible. I mean, by global basis. And then you may ask the question, what if A is not commutative? For example, if A is the Stirnov algebra, so do we have kind of a generalized global generalized theory of global basis such that you can have a very fast computation of CGGs? And the answer is yes. For any non-commutative algebra, such that I mean, my new discovery does not apply to all non-commutative algebra. I must have associated graded algebra of A such that it is commutative, and explicit. I mean, by explicit, I mean you have to know the generate a presentation of this associated graded algebra. Given this, I can develop a global basis for such an algebra. So the idea is that for example, for the Steenrod algebra, I can give a weight on this. I think it's by Doc. And you can find this in Doc's green book. And if you use this weight function to filter the dual Steenrod algebra, then you are going to get an associated graded algebra of A, which is exterior algebra. It's an exterior algebra of I'm going to call it Pij here. It's exterior algebra. There's no power, so I have no trouble of writing upper indices here. So it's an exterior algebra. So how can we compute a group? So if we have so let's say we have several elements in a free module of A, how can we compute the series of this F? The idea is that we have to form certain global basis, and so I'm going to choose an ordering on those Pij, and then because of those ordering, I can so for the exterior algebra, it's very easy to form a basis for the algebra, for the exterior algebra. Let's assume that M is a basis of the associated graded algebra, and because I fixed the ordering on the monomials, so for each M, I'm always going to write the generators in order. So this may be P1, this may be P3, this may be P7. I have to make sure that it's ordered. So then I can lift the monomial ordering. I'm sorry, I can leave the basis to A. So I'm always going to write elements of A in terms of it looks like elements of the associated graded algebra, but I know in my mind, I know that it's not commutative, but all elements are going to be like this. It's again like M plus M1 plus N1 plus M2 plus N2 plus . And then how to obtain a global basis for this. So by the Bach-Burger's original program, the way you do that is you kind of try to compute the least common multiple of Mi. And then you for example, you may multiply the first one by M2 and multiply the second one by M1. If M1 and M2 have certain kind of sorry, I have to be careful with my my multiplication here. So sorry, I'm going to put it here, M1 plus N1, M2. So I may multiply the first one by M2, the second one by M1, then I add them together so that you can kind of kill the cancel out the common leading term and get a kind of a new leading term. But because of the fact that E naught A is an associated graded algebra, then you might have new terms from this commutator. so the leading term of this is a new candidate of the new leading terms of the sum, and so that's one of the difference from the classical Grobler basis. But you have to do some additional stuff because it's an associated. It's an exterior algebra. Then there are a new way to produce the new leading term. Assume that M1 is P8, P9, for example, and you have a relation that looks like P9 times P6 plus ... And then you act because it's the associated gradient algebra is exterior. There are new way to produce a new leading term, which is that you multiply the polynomial by P8 or P9. Then because P8 square equals something in lower monomial ordering, and then you may get, so for example, if P8 square equals P4, then you may get, so in addition to the original relation, you may get P4, P9 equals something, and then you may also multiply the second one by P9. So yeah, so basically you can multiply a leading monomial with one of its generators. That's also a possible way to obtain a new leading term. So so the algorithm is quite close to the original Butzberger algorithm. So the whole idea is that the ultimate goal is that the Grobler basis you define satisfy the property that if you have let's assume the simplest case that all Fi are inside the Steenrod algebra. And then you may ask a question: what's the additive basis of this one-sided ideal? One-sided quotient. So it's an A module. It's a left A module. What's the additive basis? So the additive basis is that you just do this algorithm. You just keep producing new leadings until you can't. And then the fun part is that in the end, the additive basis of this quotient is going to correspond to all the monomials of the associated gradient algebra, such that it's not divisible by all these leading terms. I mean, divisible in the sense of the associated gradient algebra is an exterior algebra, and then yeah, you can obtain you can define Grobler basis for such a, yeah, the only restriction you must have you must know one of its associated gradient algebra, and which is explicit and hopefully small. I mean, polynomial is better than exterior is better than an algebra with a lot of relations. And but for the Steenrod algebra, it's fine. And so right now I have the program written down. So I mean, the program for computing CGGs of Fi in a free module over A, and but I'm currently debugging it. But if I'm optimistic, I think I can obtain the E2 page of atoms up to T beyond 300 in one night. Yeah, and this is it.
Well, it's getting late, and I'm going to interrupt you because I think that's a great place to stop this on that as your last word. So first of all, let me thank let's thank Weinan first of all